All right, let me make sure it's actually working. Okay, so for number 6, it says find the area of the region in between the curves y equals sine of x and then y equals cosine of x from x equals 0 to x equals pi over 2. It's probably one you should be able to do without our calculator, but it's also one that's kind of tricky anyway with your calculator. So I do want to do this one with the calculator. So in your calculator, let's go ahead and graph these. So let's graph sine of x. Let's graph cosine of x. When we graph these, we kind of know what's generally going to happen, but if you recall what we were doing on Friday when we were trying to find the area between two curves, actually, let me do a standard window here because that's probably what most of you are looking at. This is what you're going to be looking at, and if you remember on Friday when we were doing the area between the curves, what we were basically trying to do was the top curve minus the bottom curve. As you can see, and you would know this anyway, the sine and the cosine curve continue to flip-flop which one's on top as we move our way through. All right, it's constantly changing. So what we want to pay attention to in this one is the interval that I gave you. I want you to go from just 0 to pi over 2. So one of the things you want to be good at with your calculator, there's really only 4 things on the calculator that the AP test tests you on, and this is one of the 4. And that is changing your window and being able to manipulate that to get a window that actually is workable. So in our window, since we're only going to go from 0 to pi over 2, go ahead and make your x min 0 and make your x max pi over 2. Got the division sign there. Now, even when you graph that, you won't necessarily like it because now it's really distorted. You're going 1.5 horizontally, but we're 10 up and 10 down. So this is a 1.5 by 20 window. So I would also recommend making our y window also smaller. We know the amplitude of sine and cosine is a 1, so I'm just going to go -2 to 2. And then when we do this, that should now give us a nice clean graph. And since we start at 0 and we finish at pi over 2, we know that this right here is 0. We know that this is pi over 2. We don't have any extraneous graph. What we're looking at is the interval that we're concerned about. So when we now go to do this, so let's now put this on our paper. So we have this to pi over 2. Well, I'll even do it in a different color, like the book. And then that's our second one. And we now know for sure that this is 0, and then this is pi over 2. Normally then, I kind of throw this out to see if we understand which area we're actually looking for, because this is part of it, like being able to graph it. Like number 7, I obviously give you the shaded region. 6, you have to decipher the graph, understand what we're looking for. You actually have 3 different things in play right now that we need to decide what we're looking for. Are we looking for region 1, region 3, region 2, a combination of those? So it's a matter of just reading it carefully, knowing what the question is asking. We want the area of the region between sine and cosine, and it needs to be between 0 and pi over 2. So here's obviously 0. Here is our pi over 2. Shade in real quick before I do it. What are we looking for? Shade in the region that we're trying to find. All right, and hopefully when we did this, it's got to be in between sine and cosine. So the area that's in between sine and cosine should have just been region 1 as well as region 3. Region 2 is actually completely unbounded. Don't think the x-axis, unless I specifically said the x-axis up here in the setup of the problem, you really kind of interpret the x-axis isn't even there. All right, and then you can see clearly there's nothing bounded if we remove the x-axis. Now the x-axis is there so we can graph it, but it's not there in terms of the region. So those are our areas. So one of the things we talked about on Friday, if you have 2 different regions, you probably need 2 different integrals. So let's go ahead and set these up. The first integral very clearly starts at 0. That's the x coordinate where this is going to start. It's going to end at whatever this intersection point is. We're going to talk about that in a minute. But initially, the red curve is on top, the black curve is on the bottom. So knowing sine and cosine, the cosine of 0 is 1. So the cosine curve is the top curve. and sine of x is the bottom curve. So we do top minus the bottom. That's all these rectangles. If you remember all these little rectangles that we have in here that we're adding up, the top is always cosine, bottom is always sine. Then I need a second integral. That's going to take me from whatever that unknown intersection point is until the end of pi over 2. The second interval, they flip. The sine curve jumps on top, and the cosine curve comes underneath. The missing element right now is what is this intersection point? So the way we were doing these on Friday is we were setting these equal to each other and doing them algebraically. So when we set these equal to each other, you're kind of stuck a little bit. There's not a lot of work to solve this. It's really just some trig stuff, some basic unit circle stuff. Since our interval is 0 to pi over 2, right? So we're only worried about this interval on the unit circle. Within the first quadrant right there, hopefully, painting it like that, isn't it obvious which x coordinate where these are going to be the same within this first quadrant? All right, wouldn't that have to be the pi over 4? So this intersection point here ends up being pi over 4. So it's the upper limit for the first one and the beginning or the lower limit for the second integral. To save a little bit of time, I would just make sure you can plug these in. Don't take that for granted. You would not be the first person to have something like this correct on the quiz and you plug it in and you get it wrong. So at some point you might want to plug these in. We're going to have an opportunity to plug some of these in here in a little bit. But for this one, just to kind of save a little bit of time. Once that's set up, throw it into your calculator. You should get 0.828 as the overall answer. Make sure you are in radians if we start having trig functions, which obviously we do. If you're in degrees on Wednesday, that'll be a problem. Okay, you'll miss every single one that has a trig function. Okay, good with that? Remember all that stuff, hopefully. Come back to us. All right, 7 then. Find the area of the shaded region below. I forgot to label one of these. So this one right here, label this parabola, the only parabola on here. That's the parabola x squared over 4, so you'll need to know what that equation is. So as we go to set this one up, we want to find the sum, we want to find the integral. The area pretty clearly starts at the x coordinate of 0. If you recall again, like I showed in the first one, we have all these little rectangles in here that we are adding up. So as we start at 0, notice how the line y equals x is on top of that shaded region, and the parabola x squared over 4 is on the bottom. So starting at 0, we have y equals x on top, x squared over 4 in the denominator, on the bottom, not in the denominator, but on the bottom. But what we want to now be aware of, as I continue to draw rectangles in, wouldn't I eventually start, let me do it in a different color, wouldn't I eventually start also getting rectangles over here? And wouldn't these rectangles now have a different top curve right here? So even though there's only one region, it's pretty obvious when you have two different regions. And we did number 3 on Friday. I don't have it shown, but if you look, there were 3 different regions, so we needed 3 different integrals. That's pretty obvious. Here we only have one region, but we still need to set up multiple integrals. So don't just assume that there's a direct correlation there. We need to set up another integral because at this point right here, at the x coordinate of 1, between 0 and 1, the line x is on top, x squared over 4 is on the bottom. But if we move to the right of that point, so starting at 1 through 2, the top curve changes. Now the top curve in here is a 1. The bottom is still this parabola, x squared over a 4. So then those would be our 2 different integrals. That's another way we may have to set up multiple integrals at the top or the bottom curve changes, which is not unusual. Okay, something that we want to see and recognize. Okay. Again, I'm going to trust that you can do this without having to show it. We're going to have to plug some in again, like I said, in a little bit, but you should get 0.833 if you want to make sure at some point you can get this. Yeah.
Are you able to subtract it from the top area? So I just drew a small triangle.
Yeah, I suppose. Say that again now. Sorry, I interrupted.
So from point 1 to 2, I had the X above, and then I think the one underneath it. So it got that little section, and I just subtracted it from. Hard to explain, but
Here's what I thought you were, so that's why I jumped in. So, tell me what you did again.
So I found the area where X is above and the parabola is below, from 0
X
to 2.
is above, and
from 0 to 2, and then with that little bit of extra space on top, the little triangle.
Yep.
And then I just
subtracted it away.
Right.
Yeah, that would be fine.
That'd be fine.
Yeah, it should give you the same thing. Yep. All right, the next one now is we're going to throw into the calculator for sure. We could draw a cheap little sketch of this to get us going at least without a problem. Where if I do, here's sine of x, 1 minus x squared is a parabola that opens downwards, the vertex up here at 1. But for the sake of this problem, this has to be done on the calculator. So go ahead and throw that into the calculator. And I'll do that also. Sine of x, 1 minus x. Get a standard window. If you change your window, it's going to be all messed up now. So we could have sketched that and had a pretty decent idea of what this is going to look like. I'm going to zoom in a little bit. So I'm going to make my window a little bit smaller. Do 3s just so it's blown up a little bit. So this is what we're going to put on our paper. No real tricks. It's not like we have two different regions. If we look at the area, let me go ahead and draw it. The same curve is on the top and the bottom. So we're looking for this space right here. So initially it's pretty straightforward, not that it gets hard, but there is a little element that we need to be able to do. When I go to set up this integral, the parabola, no matter where I draw in a little rectangle that we're adding up the area of, no matter where I draw in my rectangles in here, the parabola is always on top, so that goes in first. And the sine curve is always on the bottom. So in that respect, it's pretty straightforward. That's pretty easy. Your issue is we now need our limits. So what we've been doing, and it's been working for us so far, we take these, set these equal to each other. So 1 minus x squared is equal to sine of x, and then we've been solving that equation. If you can solve this algebraically without the use of technology, then you are in the wrong class, okay? Because you are very, 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 very smart, okay, if we could solve this without a calculator, all right? So this now is why we definitely need our calculator. So what you're going to do in the calculator, what we need is these intersection points. So you've done this at some point. A lot of people didn't remember, but I'm pretty sure you've seen this. If not, it's not hard. We need to figure out what is this intersection point, and we cannot do it algebraically. So if we go to, notice where this says calc, we've used this a little bit before. So hit second, and then hit the trace key where it says calc up here. If you look down at number 5, you're going to see the word intersect. Since that's what we need, that's what you're going to go down to, or just hit number 5. When you hit it, it brings you back to your graph. I'll give you a second. We all need to be here. So you should see your little guy flashing at you right now. I'm going to do this intersection first. So notice how it's asking for the first curve. The first curve is just whichever one you have entered. So since I had the sine curve entered, that's why it has me on the sine curve initially. So if you did the other ones, that doesn't matter. Since there's two different intersection points, just make sure your little guy is closest to the one that you're trying to find. So once I'm pretty close right there, I'm going to hit enter. It's going to automatically jump me to the other curve, and as long as he's close, which he is, he's close enough to this one, so we know we're finding this one versus this one. Hit enter again. Then it should say guess. There's no reason we can't guess, so go ahead and hit enter. And then this is the x coordinate for where we intersect. Now, we don't want to round this. Remember, we don't want to use a rounded answer in a calculation, because what ultimately is the most important thing is our final answer has to be exact through the third decimal place right here. And if we start using a rounded answer, so if we just do a negative 0.40, actually I think it was a 409 or something, and we start getting rid of all these decimals, there's a reasonable chance if we use these rounded answers here, it's going to get off a little bit. So we can store that. So let's go to here. Now this did not work last period, so I'm going to see how this works. If it works this period. So what you want to do is, as long as this was the last thing that you found, go ahead and quit. Immediately hit store that as x. And remember, it was a negative 1.409. So when I now hit enter, you're going to see x is now stored as that negative 1.409. So if I go back to my paper, I'm just going to enter that as x, because I have that stored. Then now take a second and make sure we understood how we got that second intersection point. So do this real quick before I show it. See if you remember how we just did that. Find that second intersection point. All right. Hopefully we got it. You go to the calc menu right here. It's the second function above the trace key. So second and then trace. We want number 5 intersection. Self-explanatory there. Now you just need to get closer to that other intersection point. And same thing. Hit enter. It'll jump you to the other one. You're already close. Hit enter again. It's ready to guess. Hit enter. That's our second intersection point. So that's our upper limit. Now, this did not, I don't know why this did not work last period. We're going to try it one more time. But now we want to go ahead. Let me try something real quick. Yeah, let's quit. Exit out of that. And then now I want to store that. We don't want to do x because it'll then override this guy. So we're just going to pick a different variable. I used y last time. It did not work for some reason. If it doesn't again, I got to figure out what the deal is. I don't know what's happening. And then now I can go over here and save that as y. Yeah.
Sorry, how do you store the values in this?
So once you get them, here. So if I do second calc 5, so if I go over to this one, just go ahead and do the intersection. Did you get that yet?
Yeah.
All right, so once you get to this where you have the answer, what you now need to do is don't do anything else, just quit immediately. That's the last calculation that the calculator did. Mm-hmm. So then just right away hit store. And then store that as your variable.
All right, thank you.
All right. Is that what it is, Alex?
Yeah, so I tested it out, and the x didn't work, but when I substituted x for I, and I made I the same value.
I think we need to use this x right here. That's what I was kind of wondering. Like, we don't want to use the x variable key. We want to use a different one of these guys. All right. I think that's what the issue was, is I was kind of recalling all of that. But that's how you can kind of find all of those. In this case, even if you did round, you were going to be fine. But this should have given us 1.670. And if you had rounded, you still would have been okay with this one. Where you get into real problems is exponential functions, because exponential functions grow so quickly that any rounding at all gets your decimals off very, 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 very quickly. Okay. So being able to find these intersection points, definitely something that we want to be able to do. All right, with your calculator, because if I give you one of these, you can't solve that by hand. We've got to be able to do them on a calculator. All right, that's something on our quiz Wednesday. Certainly one of them will, at least one of them will be one where you had to do that by the intersection button. All right. All right, so now go to the next set of notes. So make sure I'm still recording here. Yes. All right. And what you're going to see at the top is where it says 7.2 continued. It says horizontal rectangle. So as you find that, let me show you what this is alluding to. So if I do this, so if I do what we did at the very beginning, when we first started with our rectangles, remember how I would say, all right, here's 0, here's 4, let's split this up into 4 rectangles. We would draw these in like this. These are considered vertical rectangles simply because we have stretched them vertically. If these guys had fallen over and now we're stretched horizontally, that's what this is alluding to when we start talking about a horizontal rectangle, okay? And it says underneath there, sometimes in order for us to find the area of a region, we may need to integrate with respect to y rather than with respect to x. This would need to occur if, A is probably the easiest to understand. What happens if I do top and the bottom, and the top and the bottom is the same exact curve? Then we obviously would have a problem because that's going to be a 0. Some of the problems we've done have required multiple integrals. The problem that we did today that required 2 different integrals, we could have done that once we know how to do this in 1 integral. So it may be easier or less work to do it with fewer integrals if possible. And then the big one is if it's just written with respect to y. So if you just look at these equations on this whole set of notes, these should just look weird. These are now x written in terms of y. This is x written in terms of y. So chances are now it's a little bit different idea, a little bit different method, and that is the idea of horizontal rectangles. So go to number 1, and what I have written, it's going to make more sense seeing it anyway. So go to number 1, and we want to graph this. So should you be able to do this without your calculator? Yes, this one anyway. But my guess, while you may be able to piecemeal this one together from previous knowledge, this you've never done without a calculator. So we'll show how you're going to graph these with your calculator. So on the calculator, let's get out of this. Get out of there. Go to, see the program button right here? Right above that is draw. So since that's a second function, we want the draw, so go second draw. Scroll on down to where it says 8, draw inverse. Hit enter, and you should be looking at this. And then you have your little cursor flashing at you. What we want to enter right here, where this is flashing, if I go back to our original problem, see how this, no, it's circle of death. This is my computer, they gave it back to me, it's re-image, it's supposed to work perfectly now. And here we go. But let's try this. See what I'm circling right here? That's our equation. So what we're going to do on our graphing calculator is we're going to enter negative, just use the variable key x squared. We should know what this looks like without a calculator, right? Is if y is squared, just before I hit enter and you see what it looks like. If y is squared, you go left or right. If you have a negative coefficient, you should go to the left. And since there's no plussing or minusing any constants, there's no shifts, your center should be at 0, 0. So if I now go back and graph this, oh man, I didn't clear the other. You're going to want to clear those other ones out. Darn it. You probably all have the same thing I have. So now go through, clear it. I'm going to have to show you right now again anyway, because now it won't be there. So I'll walk through it right now. So clear that out. So here's the draw menu right there, Zach. So since it's the second function on the program key, hit that. And then it's number 8 down there. Hit enter. And then we're just entering this again, negative x squared. And then it's going to, oops, don't want that. That's that. And it'll interpret this now as a y. And enter, and then it's that parabola opening to the left. Okay, so let's go ahead and throw that in there. And then what I want you to do real quick, let's make sure you can do one on your own before we go. See if you understood what we just did to graph this one. So now graph that second equation. So second, draw, throw all that in there. For those who are really good with their quadratics and remember all this from last year, that should also open to the left, right? Because it's a negative y squared with a negative coefficient. The bigger 3 has a bigger amplitude, so it's a more narrow parabola. So this should, when you do all that, I'll go through it one more time. So quit. Second, draw number 8, and then now we want 2 minus 3x squared. There you go. Looks like a rocket ship taking off the screen there. All right, so let me draw that in. So our vertex is here too. And this is our graph. So this is the negative y squared. When you first started graphing back in probably like 6th or 7th grade equations, your teacher may have made you label all your graphs. Might be a good idea with these to know which is which, since we got to identify tops and bottoms, and actually something a little different here. So I like to start with this one because I just went through 3 different things that could make us have to do this a little bit differently. One of the things I mentioned is, what if the top and the bottom curve are the same? So if I drew in rectangles now, like we've been doing, so if I draw in a rectangle here, isn't the top curve and the bottom curve the same exact thing for these rectangles here? So if I'm going to do top minus the bottom for this, that's a problem. So we don't want to do that. The other issue is going to be, although let me leave one of these, eventually don't I get over here, and wouldn't the top or the bottom curve have changed? Here the bottom curve was this parabola, now the bottom curve over here is this parabola. So that would imply we're going to need multiple integrals, which is generally not something we would try and do. And then the biggest thing is, just look at these, right? Aren't these written in terms of y, right? So what we're going to do instead, this is the whole title at the top of the page, we're going to draw these in as if we have horizontal rectangles. So now draw in rectangles that have fallen over and are now stretched horizontally. So whenever we've been doing all of these, if we're stretching them horizontally, now that this has fallen over, here is your height. Our height is now going horizontally, all right, if they've fallen over. So now that our height is horizontal, think about how we could identify the length of these red rectangles. Couldn't we now do whatever the value is right here, and this would now be an x value, minus whatever the x value is right here. Whatever the difference in those values are, same down here, whatever the value is at this point, minus whatever the value is at that point, the difference would have to be how long those red rectangular heights are. Okay, does that make sense? So when we now do this, go ahead and set up your integral. When we do horizontal implies, we've now got to be doing a right minus a left. So the curve that's on the right is always the 2 minus 3y squared. Minus the curve on the left is always this parabola, negative y squared. These are our heights. So let me label this again. And we now need our base. So think back to, let me just draw in one of these parabolas so it makes a little more sense this way. So let's say this was our region. And let me say we go back to what we did at the very beginning when we did all this. Remember, we drew our rectangles in. Another rectangle here. Isn't our base now, here's our base right here, here's our base right here. Instead of doing it this way, where our base is always the change in x when we draw our rectangles in, aren't our rectangles base now going to be the change along the y-axis? So instead of doing our base as the change in x, now our bases would be measured as the width along the y-axis, so dy. Your limits, now that we're doing y's everywhere, better be y variables. So we want to know what are our 2 limits. We can solve that the same way that we've been solving them. Just set those 2 equations equal to each other. Create a little room here. So the negative y squared equals 2 minus 3y squared. solve this. So 2y squared equals 2. Sorry, I'm going to rush. This should end up being a positive negative 1. So our limits are negative 1 to positive 1. Understand what that means graphically. We have found this intersection point here and this intersection point here. So we have now found that we start at the y value of negative 1. And starting at that y value of a negative 1, we start stacking all of these horizontal rectangles on top of each other until we hit that top intersection point right here. And we have found that to be a positive 1. When we then do the integral and add all of those, I add all these red rectangles whose heights are rights minus lefts, so we're going to add these guys. That should give us our answer. And then the last thing, real quick, your calculator doesn't, I don't think I have time to show you, the calculator doesn't know that these are y's. So when you do math 9, there's no reason to use the y variable, just use the regular variable key x. And it will evaluate it the exact same way that the other page did. So when we do that, this should give us 8/3. Okay? Now, bell's gonna ring any second now, but what I'm gonna do is make the video for 2 through the rest of these, probably 20, 25 minutes worth of stuff. If you have any questions, reach out to me, but this is what we're gonna quiz on Wednesday, so try to make sure you watch that before Wednesday so you have an opportunity to ask any questions before we were to take it, okay? Okay, we'll see you guys. Enjoy your day off tomorrow. We'll see you on Wednesday. All right, so number 2, this should be where everybody is leaving off. Or I'm sorry, 7th period to be leaving off, and then 3rd period you guys can jump ahead to the next page. So number 2, you're going to find the area enclosed by x equals y cubed minus a y. So a couple things real quick. I've done a little calculations here, but one of the ways you can clear your drawing, because you probably still have your drawing from number 1 that we just did, if you go back into your draw menu, the very first thing you're going to see here is it says clear draw. If you hit that clear draw and then hit enter, done, now you're not going to, if we hit graph, your drawing's not going to be there anymore. The only thing that you're going to see are these 2 equations. If you don't do that, then you're going to still see the previous drawing from number 1. So you want to do that again. So it's just second draw and clear draw. So for this one, we're going to graph y cubed minus a y. So the way we graph those, you're going to do the draw option. So second program. You're going to hit number 8 down here, draw the inverse. And then that was y cubed minus y. And then you'll hit enter. And then that's what that graph is going to look like. So that's what I'm going to put on our paper. So it looks like this. What we were wanting is the area enclosed by y cubed minus y and x equals 0. X equals 0 is just your y-axis. So if we look at our curve and we look at the y-axis, we have 2 different regions here. So similar to what we did last week where we may have had some multiple regions, that's what we've got going on here. I guess we did one today too with the sine function and cosine function. So what we talked about in the previous problem, if I do these as vertical rectangles, notice how the top curve and the bottom curve are the same. That generally tells us that we don't want to be doing that. In addition, the way this is written in terms of y implies we're going to do this horizontally. So we're going to draw our rectangles in horizontally. All right, so there's our horizontal rectangles. And if I want the area of this, any rectangles down here, again, since we're horizontal, this is even better to kind of see how this is the change in y. Let me actually draw these a little wider. We can see this is our width here along the y-axis. So when we go to define our height times our base, the base of all these, if we were doing Riemann sums, we would have said was the change in y, whatever that would have been defined to be. But now that we're doing the definite integral, that actually does add them all up for us. So this is our dy. The height, since these have fallen over, is whatever curve is on the right. So if we look over here, y cubed minus y is on the right, and then 0 is on the left. However, we have to go up here as well. And if you notice now, the right curve is now the y-axis, and the left side is now the curve y cubed minus ay. Okay, so here's now our left, here's now our right. So since our right and left curve has changed, we need to set up another integral that shows 0 as the right side, and then the y cubed minus y as the left side. The last part that we're missing is the limits. So what we need to figure out is, where do we start at down here? Where do we finish at up here? And where do they switch in the middle? So that's just the intersection of y equals 0, and x equals 0, and x equals y cubed minus y. So set those equal to each other. Pull out your common factor of y, and then we can see just from here, we intersect at positive 1, negative 1. So this is the negative 1. Up here is our positive 1. And then the one that we kind of just knew by looking at our graph or our calculator, if that's how you graphed it, oh boy, is the 0 that would have been right there. All right, so this is our 0. So this first interval or first region that we're looking for would go from a negative 1 to 0. So we would have started stacking rectangles in here. The integral adds them all up for us. But then starting at 0 through 1, the right-hand side became the 0. The left-hand side became the y cubed minus y. Throw it into your calculator. When we throw that into our calculator, that should give us 1/4 for each of them. So overall, the area is 1/2. Okay. Three. I'm going to trust we can now graph these on the calculator. Both of these we could probably do without our calculator easy. But if you have it, go ahead and use it. Here's x equals y squared. We could just rearrange this real quick, right? Put this in the slope-intercept form and see that our y-intercept's a -6 and our slope is a 1. Or just use your calculator. We know how to do this on the calculator now. We do get an interval this time, so the first time with these I've given you this. So we only want to go from y values starting at 0 to 3. If I hadn't given you that, then this would have been our area. This is the region enclosed by those two graphs. But clearly if I'm going to start at the y value of 0, then I don't want anything down here. So our area will start right here at 0, and then we're going to go up to 3. So what we need to know is, what is this intersection point? We're hoping that this is a 3. If it's not a 3, think about what that would now mean. If this continued on, then we could end up getting some area in here as well if we have this horizontal line that boxes us in. So what we really want to know, what is this intersection point? How does it relate to the interval that ends at 3? So let's take these guys, set them equal to each other. So you do y squared one of my pens not working. Oh, that's why. So sorry, y squared equals y plus 6. Set those equal to 0. Do a little factoring real quick. We get 2 intersection points. One of them would have been the -2. That would have been the intersection point down here, was this -2. But since I gave you this interval, we don't have to worry about that one. And then we find the second intersection point is 3. So that is nice, because that does then tell us that this dot up here where they hit, that is going to have a y coordinate of 3. So the area we are looking for is this one. When we now kind of decide, are we doing tops and bottom or right and left? There's a couple of giveaways. One, the way this is written, it's a function in terms of y. That implies we probably want to do right and left. The other issue is, if I were to draw in rectangles here Notice how the bottom curve is going to change. Here the bottom curve was the x-axis, but as I move further right, the bottom curve is going to become this line. So the fact that the bottom curve changes, we would need multiple integrals versus, let's say we drew these in horizontally. Do this in a different color. If I go horizontal rectangles, notice how the right-hand side and the left-hand side would never change. That's going to allow us to do this with one integral versus two integrals. So that's our route. So we're going to set up our integral. So the sum. The right-hand side is always the line y plus 6. The left-hand side is always the parabola y squared. So this is really just the right side minus the left side. That's the height of all of our rectangles. And then if I multiply by the base of all of these, since it's horizontal, the width of my pen, or my pen here in red, would be measured along the y-axis. So that's the change in y. So dy. And then we kind of already know our limits, right? We start at the y value of 0. That would have been right here where we would have drawn our first rectangle. And then we continue to stack these rectangles. Starting at 0, we stack until we get to the very top of 3. That's why it's a solid, continuous shape. And our upper limit then becomes a 3. Throw that into the calculator. And I believe this is 27 halves. Okay. Now, number 4 is the big one. So as you finish this, we go to number 4. Number 4 is the big one. What we do all chapter, we're going to add some layers to what we're doing right now. But what will always be important to understand, and if you can understand this, this chapter typically goes very well for people, is the idea that if I look at this equation, x equals y squared, this is what we have been doing today. The whole right minus left horizontal rectangles. However, if we look at the next equation, where it's now y equals x minus 2, that is what we had done on Friday. And when we did these on Friday, that was implying a top minus a bottom. So we want to recognize something's afoot here, like they're not compatible. So let's draw these. X equals y squared. If you need your calculator, go ahead. So here's x equals y squared. And then y equals x minus 2, y-intercept of a negative 2, slope of 1. So similar looking graph to the previous one that we did. I tell you first quadrant. So because it's in the first quadrant only, similar again to the previous problem, looks the same. So what you now need to do is decide what's best. Because if we're going to do tops and bottoms, then we want everything to look like y equals whatever. If we're going to be doing rights and lefts, then we want our equations to both be x equals whatever. So we have to decide which method is going to be the best and the simplest and the shortest. So if we try to do tops and bottoms, similar to what I drew in the previous question, if I do the top curve, eventually I get to this point right here. And while the top curve stays the same, notice how now the bottom curve has changed. We don't want that. It will work, but if at all possible, we don't want to have to be setting up multiple integrals if we could do it with one integral. So if you look at the red, notice how the bottom curve is going to change from the x-axis to this line. So that's going to require two different integrals. However, if we do them horizontally, so let's say I draw in some horizontal rectangles. So now we're thinking rights minus lefts. If I look at that, isn't the right-hand side of all of these horizontal rectangles, isn't the right-hand side always this line? So that doesn't change. And the left-hand side of all of these horizontal rectangles would always be this parabola. So that does not change. So if I do it horizontally, that means I can do it with one integral versus two integrals if I try to do tops and bottoms. So one, simpler, there's less work, so that's the route we're going to take. So we're going to set up our integral. We said if we do right minus left, that's our best bet. That means our base for all of our rectangles, let's hope we understand this now. If I look at this marker, this pen right here, notice how this one, while it's not technically up against the y-axis, but if we look at how that lines up against the y-axis right here, the width of the base would be measured as the change in y. Whatever the width is from this mark to this mark, that's the width of my orange rectangles, the horizontal rectangles. So because of that, the base of the horizontal rectangle is the change measured along the y-axis. If I go to the next one here, notice how wide this one is. That width would be measured along the y-axis. So change in y is our base. That's why everything has to be in terms of y. So when I now go to set this up, the right-hand curve is this line. And here's probably our first instinct, is to take the line x minus a2 and then subtract the left-hand side, which is the parabola y squared. But then that hopefully just looks weird to you, hopefully, because what we certainly do not ever want right now is to have x's and y's together. We have multiple variables right here, and that's something we really want to avoid. So what that's going to require us to do is the line y equals x minus a2. If we're going to do this horizontally, and again, this is the biggest thing to keep straight. It's the only thing really that people get confused on in this chapter, the main thing. I want to solve this real quick for x, because I can now define this equation as x equals y plus 2. So now, doesn't this equation, x equals a function of y, and this equation where I have x equals a function of y, now those are compatible? So that's how we want to define that line as a y plus a2. Hopefully that makes some sense. If we were doing them vertically, we want to do top and bottom. We would have had to have solved this one for y so that it's written as y as a function of x. But in this case, we're doing it horizontally. Everything needs to be in terms of y. That means our limits need to be in terms of y. The lower limit's easy. I said first quadrant only. So that means the y needs to start at 0. And then we would just need to figure out what this intersection point right here is. So we can now do that by setting equal the two equations, the y plus 2 version equal to the y squared. And then we just solve this. You can see one of the intersections would have been the -1. That's this guy down here. But since we were told first quadrant only, we're going to not have to worry about that one. The other intersection is 2. That's the point up here. So we now know that this integral stops at 2. Okay. Throw that into the calculator, and that should be 10/3. All right, last one I'm going to have you do, number 5. Typically, I would just have you try this on your own. So if you wanted to pause me, see if you can do this on your own. Not a bad thought. We're going to graph this, x equals a negative y squared. The reason I have you do this usually on your own is because it's very similar to one we've already done. That's our first one. X equals a negative y squared. Notice how, too, before we get too far along, x is written as a function of y. Same here, x is written as a function of y. So these are both implying that we want to do this horizontally. Okay, they're compatible. Shouldn't have to rewrite any of these equations. Graph this one, so now we're over here at 8. It's a more narrow parabola that opens to the left. The area that's enclosed by them is this region here. So the way these are written imply we want to do it horizontally. As long as the right and left hand side are always the same, we can do it in one integral. So if I draw in some rectangles in here, you'll notice the right hand side is always the parabola that goes through 8. The left hand side is always that negative y squared parabola. So we can do this in one integral. We'll get our limits here in a second. The right hand side of all these red rectangles is the 8 minus 3y squared. So that goes in first. Minus the left-hand side, which is this negative y squared parabola. So minus the negative y squared. And then the width of all of these is the change in y. Because again, just look at my red marker here. See how it's going through the y-axis? So whatever the width is from here to here, that's how wide that rectangle would be. So our width is measured as a change in y. And then our limits would just be whatever the y-coordinate is up here to whatever the y-coordinate would have been down here. So we need to figure those two things out by setting the equations equal. Should be pretty good at this by now. Solve that. And we find they intersect at -2, +2. So -2 is the lower limit, +2 is your upper limit, and then that should end up being our integral. That's the gist of it. Number 6, not a big deal. It's something that we've done before. I don't necessarily need to do that right now, so you should be good. So if you have any questions, reach out. Hopefully this will make some sense to you as you go through it. If you have everything in terms of x, it's top and bottom. If everything is written in terms of y, it's right and left. If you have some written in terms of x, one written in terms of y, then chances are you're going to rewrite one or the other. All right. So with that, I'm going to call it the end of the video. Again, any questions, reach out to me. Enjoy your day off Tuesday, and then we will see you guys all on Wednesday.